Dear students, last class we completed the introduction of the signals. Today in this video we will discuss about elementary signals. Elementary signals which play vital role, important role in the study of signals and systems. These elementary signals serve as basic building blocks for the construction of more complex signals. In fact, these elementary signals may be used to model a large number of physical signals which occur in nature. These elementary signals are also called standard signals. The standard signals are unit step function, unit ramp function, unit parabolic function, unit impulse function, sinusoidal function, real exponential function, and complex exponential function. The first one we will discuss about unit step function. The step function is an important signal used for analysis of many systems. The step function is that type of elementary function which exists only for positive time and is zero for negative time. It is equivalent to applying a signal whose amplitude suddenly changes and remains constant forever after application. Suppose this is the unit ramp signal. Unit ramp signal. So this is that is the for positive values it is 0 1 amplitude equal to constant it is 1. For negative values it is 0. Similarly, the shifted version of the unit step signal like this n minus k. So here n t minus a. So it is 1. Here u of t you can consider u of t minus 0. Okay, u of t minus 0. U of t minus 0 for 1 for t greater than or equal to 0, here 0. But here in the u of t minus a, instead of 0, here it is a. So the time is the signal is exist for t greater than or equal to a. Okay, please observe this. Next, this is the graphical representation of the unit step signal, and this is a graphical representation of the shifted version of the unit step signal. And here next, unit ramp function. The continuous time unit ramp function R of t is that function which starts at t equal to 0 and increases linearly with the time and is defined as R of t equal to t for positive values of t. And that means here for t equal to 0, the R of t equal to 0. Okay, and here is the R of t y-axis and the x-axis is the t. T is the independent variable, R of t is the dependent variable which depends on the t. So at t equal to 0, the R of t equal to 0. At t equal to 1, R of t equal to 1. At t equal to 2, R of t equal to 2, and so on. So if you draw the signal appear like this, R of t. It is a unit ramp signal. So here we have the relation between the unit step signal and unit ramp signal. R of t is equal to t into u of t. So from this you can derive the unit ramp signal, then you can get the unit step signal. Similarly, if you integrate the unit step signal, then you can get the ramp signal. So as shown in these equations. And this is the graphical representation. And this is the same R of t minus a, shifted version of the time shifting version of the ramp signal. So this is the discrete version of the R of t and discrete version of the R of n minus 2. Next, the unit parabolic signal. The continuous time unit parabolic function p of t, also called unit acceleration signal, starts at t equal to 0 and is defined as like this: p of t is equal to t square by 2 for positive values of t. For negative values of t, the amplitude of the parabolic signal equal to 0, like this. Okay, so for positive values of t, the signal is what? T square by 2. Okay, t square by 2 for positive values of t. For negative values it is 0. Similarly, if you shift it to a units, t minus a means right side and a positive t axis, the signal appear like this. So here also it is a t minus a whole square by 2. So this is a shifted version of the signal. So similarly we can derive the derivation as like ramp and unit step. So here parabolic and relation between the parabolic and unit step signal. So from this relation you can find out unit step signal, that is by differentiating the parabolic function 2 times. That is, you can apply the second order derivative to the parabolic, then you can get the unit step signal. Similarly, you know u of t, but how will you find out this parabolic signal, unit parabolic signal? By doing second order integration to the unit step signal, then you can get the parabolic signal like this. Observe this. Next, unit impulse function. So the unit impulse function is the most widely used elementary function used in the analysis of signals and systems. The continuous time unit impulse function del of t, also called Dirac delta function, plays an important role in signal analysis. It is defined as, so here, so that is value at t equal to 0, the amplitude equal to 1, so it is a 1. So that value here like this. Here, this is the graphical representation of the unit impulse signal. So that is the signal is exist at only one value of t, at especially t equal to 0. So that is here. So t minus a, if you say, so then del of t and del of t minus 0, isn't it? So t is existed, wait, t is existed at t equal to 0. Here t equal to a, because t 0, in the 0 place a is there, so that is a, unit impulse function. These are the properties. So already you know that the unit impulse function exists at only at a single value, especially at t equal to 0. So that is, if you see del of t or del of minus t, both are same. So it is a even function. And if you see, evaluate this expression, minus integral to integral, minus infinity to infinity integral, x of t del of t dt, the entire function is non-equal to 0 at t equal to 0 only. So that's why x of 0. So similarly the other properties. So if you see, you can understand very easily. So these are the graphical representation of the discrete impulse function. And next very important signal is the sinusoidal signal. A continuous time sinusoidal signal in its most general form is given by x of t equal to a sin of omega t plus phi. Sometimes in the signals the phi won't be represented. So that's why simply a sin omega t. Here a is the amplitude and omega is the angular frequency. So and it is also repeated, it is a periodic signal. So sinusoidal signal is a periodic signal. So the period equal to 2 pi by omega naught. So where you know that omega equal to angular frequency 2 pi radians, 2 pi into f. Okay, and omega equal to 2 pi by t. Hence t, the fundamental period t equal to 2 pi by omega naught. Okay, so I mean it is a periodic signal. That means the signal is repeated at regular intervals of time. So this capital T is a fundamental period, and this is a discrete sinusoidal signal. And next to come to the real exponential signal is very important. So e powers, the signal represented, mathematical or functional representation of the signal x of t is equal to here a into e power alpha t. A is the amplitude, considered as a 1 or 2 anything. So alpha is the positive value. If alpha equal to 0, the signal appear like this. If alpha equal to positive value, the signal is exponentially increases. If alpha equal to negative, the signal is exponentially decreases like this. Figure A, figure B, and figure C. And a complex exponential signal. So like here real exponential signal, the power equal to real number, okay, alpha, but here it is the power is the complex number s. You can say sigma plus j omega, then you have to substitute s equal to sigma plus j omega in this equation, then you can get this example. And if you enter these values in the your notebooks, then you can understand clearly. It's a very simple subject, but you need to require more practice. So the signals are appear for various values of s like this. Next, rectangular pulse and signum function. It's very important, signum function. So for positive values the amplitude equal to 1, for negative values the amplitude equal to -1. Next, sync function. Sync function, it is a sin t by t. So for different values of t, if you draw the different values of t, then in between sync t and t, the waveform or graph appear like this. You can observe the maximum value at t equal to 0 here. So this is the minimum value that equals. Okay, so this is all about your elementary signals concept. Thank you, students. I can share this content in the cards. Please download it. And next topic, it is operations on basic operations on signals. Okay, thank you once again. We will meet again in next video. Thank you.